Artemis 2 is over, but the program it belongs to is not. Artemis 3 is currently scheduled for no earlier than 2028. The logic of these missions leads in one direction: Mars. Mars requires a crewed transit of 7 to 9 months through deep space radiation, followed by a surface stay of roughly 500 days waiting for the planets to realign for a return window. None of that is survivable without first understanding what long-duration deep space exposure does to the human body. The Moon is close enough to abort from. Mars is not. Artemis 2 provided 10 days of data. The missions that follow will provide months. Every flight gets longer. Every system gets tested harder. And every data point closes the gap between where humanity is and where it is going. Oxygen makes up less than 0.2% of the atmosphere of Mars, compared to 21% on Earth. A human being exposed to the Martian atmosphere without a suit would lose consciousness within seconds, not from suffocation alone, but from the pressure. The atmospheric pressure on the Martian surface averages around 600 pascals, less than 1% of Earth's sea level pressure. At that pressure, the nitrogen dissolved in your blood would begin to come out of solution, and the moisture on the surface of your lungs would start to evaporate. The surface is bathed in ultraviolet radiation and cosmic rays that Earth's magnetic field and thick atmosphere normally block. Mars lost its global magnetic field billions of years ago when its core cooled and solidified, and its atmosphere thinned progressively after that, stripped away by solar wind over hundreds of millions of years. What remains is a cold, irradiated near vacuum that is chemically hostile to unprotected biology. Mars is not hospitable now, but the geological and chemical evidence suggests it once was. Liquid water, a thicker atmosphere, possibly a magnetic field strong enough to create conditions where microbial life could have emerged. Finding out whether it did, whether life arose independently on two planets in the same solar system, is arguably the most consequential scientific question in human history. That question cannot be answered by a rover. It requires humans on the surface making decisions in real time with the full range of biological intuition that no remote-controlled machine has ever replicated. at the data. Images taken by Perseverance rover on April 14, 2026. You can see abrasion marks. These are not natural formations. They are traces of deliberate mechanical action, the imprint of a machine designed, built, and operated by humans, working millions of kilometers away. Look at those massive rises along the rim and within Jezero Crater. They are not random debris. They are the result of two processes layered across deep time. First, the impact that formed the crater itself. When a large body struck Mars, it excavated and uplifted rock, throwing material outward and creating the elevated rim and fractured blocks that still define the landscape. Second, water. Long after the impact, Jezero became a lake basin. Rivers carried sediment into it, building a delta, not a flat sheet, but a thick, sloping accumulation of sand, silt, and clay. Now shift to Gale Crater, where Curiosity rover has documented formations that do not resemble simple terrain. Thin, repeating layers stack with consistent spacing. Ridges cut across them at sharp angles. These are not chaotic deposits. They point to cycles: deposition, burial, chemical alteration, and erosion acting in sequence. Some structures resemble mud that cracked and was later filled. Others look like minerals precipitated from groundwater moving through the rock long after it formed. The key detail is persistence. The same patterns appear across different locations and elevations, suggesting stable environmental conditions that lasted far longer than a transient event. These formations are not anomalies. They are signatures of a planet that once had active surface and subsurface processes operating over extended periods. Among the more peculiar textures captured by Curiosity rover are surfaces broken into small, repeating cells, a pattern you could reasonably call honeycomb weathering. On Earth, similar structures form where salt, moisture, and temperature cycles slowly break down stone from within, grain by grain. On Mars, the mechanism is still debated. It could involve sublimating ice, salt crystallization, or long-term wind abrasion exploiting microscopic weaknesses in the rock. A human geologist standing in Gale Crater would not just document these structures. They would test them, break them, follow them across terrain, change hypotheses in real time. Sooner or later, someone will stand there and do exactly that. What they will find and how it will reshape the questions we are asking now is still unknown.